So here we're going to be solving October-November 2021, paper 21. Okay. So let's start. Now question number 1 says, sulfides are compounds that contain sulfur but not oxygen. Carbon disulfide is a volatile liquid at room temperature and pressure. State the meaning of the term volatile. So the term volatile over here means that it evaporates easily, or it easily turns to gas. Okay. Draw a dot and cross diagram of the CS2 molecule. So over here, when we talk about CS2, we know that CS2 is in the same, sulfur over here is in the same group as oxygen. So CS2 probably has a very similar structure to carbon dioxide. What that means is that carbon has a double bond with 2 sulfur atoms. So we have to draw this dot and cross diagram here. Now let's say that we're going to use X for carbon and we're going to use dot for sulfur. We're just going to include a key over here for our dot and cross diagram. So what we have is we have carbon, right? It's making a double bond. It's making a double bond with this sulfur, and it's making a double bond with this sulfur, right? Now carbon only has 4 outer electrons, those are the 4 X's over here. Sulfur has a total of 6 outer electrons, just like oxygen. We've only shown 2 for each sulfur, so we need 4 more electrons on each sulfur, like this, right? So here's the dot and cross diagram for carbon disulfide. You can draw it like this, or you can draw it with the circles. They're both acceptable, okay? Suggest the bond angle in a molecule of CS2. Carbon disulfide is very similar to carbon dioxide, right? So that means that we have a 180-degree bond angle here. And since carbon is just bonded to 2 atoms here, the total number of atoms around carbon is 2, and there's no lone pair. So what we need is 2 hybrid orbitals. So the hybridization of this carbon atom must be sp hybridization. It's sp hybridized, okay? CS2 is a liquid under room conditions, while CO2 is a gas. Explain what causes the difference in the physical properties between CS2 and CO2. Now, CS2 and CO2 are both linear molecules, and they're both non-polar. There's no net dipole. So why does CS2 have a greater boiling point than CO2? Now, since they're both non-polar molecules, they both have van der Waals forces due to instantaneous induced dipoles, right? But because CS2 has more electrons, it has stronger van der Waals forces. So we can say over here that CS2 has more electrons in a molecule, right? And therefore we have stronger van der Waals forces. Van der Waals forces due to instantaneous dipole, induced dipole interactions. Okay, you can say induced dipoles, or you can say ID interactions. You can use the abbreviation here as well. All right. Part B. The enthalpy change of combustion of CS2 is represented by the following equation. Define the enthalpy change of combustion. So for enthalpy change of combustion, right, by definition is the enthalpy change when 1 mole of a particular substance or 1 mole of a particular reactant is being combusted in excess oxygen, okay? So the enthalpy change of the combustion is the enthalpy change when 1 mole of a substance, okay, is being combusted or is combusted completely, okay? You have to say it's complete combustion or in excess oxygen. In excess oxygen. Okay? So the key words over here that we have 1 mole of a substance being combusted, it's complete combustion, and we have excess oxygen. All right. Part 2. The table shows the enthalpy changes of formation of CS2, CO2, and SO2. Use the data in the table to calculate the enthalpy change of combustion of CS2 in kilojoules per mole. Show your working. So let's actually take the equation that they've given us. Okay, we have to calculate this enthalpy change over here. We have to calculate this enthalpy change over here. So this is the equation that we have, right? And what I want to do is they've given me formation data for carbon disulfide, for carbon dioxide, and sulfur dioxide. So now if I was to draw a Hess cycle here, right? In the first box I have the reactants. In the second box I have the products. Now since they've given me formation data, if I want to construct a Hess cycle, what do I have in the third box over here? If they've given me enthalpy of formation data, what do I have over here? In the third box, we're going to have elements. So you can just say elements over here. You don't have to give me the individual elements. You can just write elements. Since they've given me formation data, we know by definition that the enthalpy change of formation is when 1 mole of a substance is formed in its standard state from its constituent elements in their standard states. So now we have to calculate this enthalpy change. Let's call this X, right? And they've given me formation of CS2. So formation by definition is from elements to that substance. So that will be plus 89.7, right? What's the formation for oxygen gas? This is just an element. So the formation for oxygen gas will be 0, right? We have formation of carbon dioxide, that's negative 394. Again, that will be from elements to carbon dioxide, that's minus 394, right? And we have formation of sulfur dioxide, which is negative 297. But with this value, what would this value be? Would it be negative 297? No, in this case, we're forming 2 moles of sulfur dioxide, so that will be 2 times negative 297, right? Now, the idea here is this. Either I can go from elements to reactants, and then reactants to products, or I can go directly from elements to products, right? This is a Hess cycle. So the idea here is either I can convert the elements to reactants and then form the products. That enthalpy change over here will be 89.7 plus X, right? And this is equivalent to going directly from the elements to the products. So that will be negative 394 plus 2 times negative 297. So what does X come out to? So this enthalpy change over here comes out to negative 1077.7 kilojoules per mole. So the 3 significant figures, that's negative 1080 kilojoules per mole. Okay. You can also write this value over here. It doesn't matter. I'm just writing the value to 3 significant figures here. All right. Now for this particular question, guys, if you guys remember, in this particular question, they haven't explicitly asked you to draw a Hess cycle. So what's the formula you can use to calculate this enthalpy change? Does anyone remember? What is the enthalpy change of a reaction in terms of formation data? For any reaction, what's the enthalpy change if they've given you formation data? It is the enthalpy change of formation of products minus the enthalpy change of formation of the reactants. Okay, if they've given you formation data, for any given reaction, अगर आपको products और reactants का formation data दिया हुआ है, if they've given you the formation data for products and reactants, the enthalpy change can simply be calculated by taking the formation of the products and subtracting the formation of the reactants. So here, your enthalpy change would be negative 394 for carbon dioxide as a product, plus 2 times minus 297 for sulfur dioxide, 2 moles of sulfur dioxide, and then you subtract the formation of the reactants. So that'll be minus 89.7. We're going to get the same answer here. Okay. All right. Hydrogen sulfide gas is slightly soluble in water. It acts as a weak acid in aqueous solution. State the meaning of weak acid. A weak acid is a substance that only partially ionizes. It only partially ionizes or partially dissociates, right, in solution. So that's the meaning of the term weak, and the meaning of the term acid is to form H plus ions. Now, I want to clarify one thing. When we say we have a weak acid, it's not the same as saying it's not soluble. So I'll give you an example. So for example, if you take the example of magnesium oxide, right? Now magnesium oxide is a strong base. Even though it barely dissolves in water, so in water, for example, if I dissolve magnesium oxide in water, it forms magnesium hydroxide. Now, even though it only dissolves very partially, even though it's very insoluble, right? Whatever does dissolve, let's say you had like, let's say you had like 100 units of this, but only one of them dissolved. Whatever does dissolve will ionize completely. Whatever does dissolve will ionize completely. So in this case, for magnesium oxide, the pH of the solution won't be very high because magnesium oxide is not very soluble. However, even though it's insoluble, it's still a strong base. So whatever does dissolve, it ionizes completely. जो कुछ dissolve किया, वो पूरा ionize करेगा. So even though it's insoluble, it's still a strong base. Okay. So solubility is not the same as the strength of an acid or a base. When we talk about the strength of an acid or a base, it's basically saying whatever did dissolve, जो कुछ dissolve हुआ, to what extent did it ionize? So magnesium oxide, even though it barely dissolves, it ionizes completely. Okay. So you may say, yaar, iski pH zyada high nahi hai, so it must be a weak base. No. Iski pH isn't high because it doesn't dissolve too much. But whatever does dissolve, ionizes completely. So therefore, it is still a strong base. Give the formula of the conjugate base of H2S. So let's say that I have this weak acid here, H2S. That means it only ionizes partially, right? To form H plus and HS minus. The conjugate base is what forms when the acid loses a proton. So the conjugate base over here is HS minus. The conjugate base of this acid is when this acid loses a proton, what does it form? Okay. And the conjugate, if you look at this base over here, HS minus, its conjugate acid is H2S. What do we produce if this base gains a proton? That is the conjugate acid. Okay. So H2S and HS minus are a conjugate acid base pair. HS minus is the conjugate base of H2S. So when H2S loses a proton, it forms HS minus. And H2S is the conjugate acid of HS minus. H2S is formed when HS minus gains a proton. Okay, so here the conjugate base would be HS minus. H2S aqueous reacts slowly with oxygen dissolved in water. The reaction is represented by the following equation. Explain with reference to oxidation numbers why this reaction is a redox reaction. So my first question is, what substance over here is being oxidized? Sulfur is being oxidized here. The oxidation number of sulfur over here is, we know hydrogen is +1. So we have 2 times +1 and sulfur is, let's say, X, and that's equal to 0. So sulfur over here is -2, right? So sulfur is being oxidized from -2 to 0. So there's an increase in oxidation number. So we can say that sulfur is oxidized from -2 to 0. Okay. And what's being reduced here? Oxygen is being reduced. Oxygen is going from 0 to -2. So we can say that oxygen is reduced from 0 to -2. So sulfur over here is oxidized from -2 to 0. In other words, hydrogen sulfide is the reducing agent. It's undergoing oxidation. And oxygen is reduced from 0 to -2. In other words, it's the oxidizing agent. Okay, in this reaction. So the compound arsenic sulfide, As2S3, is a common mineral. And when it's heated strongly in air, in other words, it's combusted, we form arsenic oxide and sulfur dioxide. A sample containing 0.198 grams of arsenic sulfide is placed in 0.1 decimeter cube of pure oxygen, which is an excess, in a reaction chamber connected to a gas syringe at room temperature. The reactants are heated until no further change is observed. The products are then allowed to cool at room temperature. Calculate the volume in decimeter cube of gas present at the end of the experiment. You can assume that all gases will occupy 24 decimeter cube per mole under these conditions. So we're assuming that this is carried out at constant pressure and temperature, and this is carried out under room conditions. Now at the end of this experiment, what we're going to have is we're going to produce sulfur dioxide, and we're going to have oxygen left over because they've said that oxygen is in excess. Okay. So again, what we want to do is we want to figure out the volume of oxygen and the volume of sulfur dioxide left over. And the first thing we want to do is we want to figure out the number of moles of As2S3, because that's the limiting reactant. So we can say that the number of moles of arsenic sulfide is equal to the mass divided by the molar mass. The mass is 0.198 grams, and the molar mass is, the molar mass of arsenic over here is 74.9. So we have As2, so that's 2 times 74.9, okay? Plus, we have 3 sulfides here, so we have 3 times 32.1. So then how many moles do we get for As2S3? So here we get 8.0455, so that's 8.046 times 10 to the power of negative 4 moles. So we can say over here that we have 8.046 times 10 to the power of negative 4 moles of As2S3. In other words, arsenic sulfide के हमारे पास इतने moles हैं. So then, can we calculate the number of moles of oxygen that reacted? We can say over here that for every 2 moles of As2S3, for every 2 moles of As2S3, right, 9 moles of oxygen react. So if I have 8.046 times 10 to the power of negative 4 moles of this, how many moles of oxygen react? Using the molar ratios from the equation. So here we get, for the number of moles of oxygen that react, we get 3.62. We get 3.62 times 10 to the power of negative 3 moles, okay, of oxygen react. So then, can I figure out the volume of oxygen that reacted? Remember, initially our volume of oxygen initially was 0.1 dm cube, right? So can I say that the volume of oxygen over here that reacts is equal to the number of moles times 24 decimeter cube? So that would be 3.62 times 10 to the power of negative 3 times 24. So what volume of oxygen reacts? So this is equal to 0.08689 decimeter cube react. So then what's the volume of oxygen left? What's the volume of oxygen left? Can I say over here that the volume of oxygen left is simply 0.1 minus 0.0869 or 8689? Since we know how much we started with and we know how much reacted, the volume of oxygen left is, we get 0.01311 decimeter cube. So that's the volume of oxygen that we have left over, right? We can also find now the volume of sulfur dioxide that was produced. Right? We know over here that if we can actually do that, we can compare the volume ratios directly for gases. Do you guys remember that for gases, the molar ratios are the same as the volume ratios? So if over here we had 0.08689 decimeter cube of oxygen reacting, what's the volume of sulfur dioxide that was produced? Right? We can say over here that for every 6 moles of oxygen that react, for every 9 moles of oxygen that react, 6 moles of sulfur dioxide are produced, right? That's given to us in the equation. For every 9 moles of oxygen that react, 6 moles of sulfur dioxide are produced. So we can say that if over here 0.08689 decimeter cube reacted, what's the volume of sulfur dioxide that was produced? Remember guys, for gases, the molar ratios are the same as the volume ratios. Only for gases, we can directly compare volumes using the molar ratio. So what's the volume of sulfur dioxide that was produced? We get 0.0579 decimeter cube. So what we have is we have the volume of oxygen left and we have the volume of sulfur dioxide. So what's the total volume of gas? That is 0.0131 plus 0.0579. And we should get 0.0 0.071 decimeter cube. All right. And this is the answer to three significant figures, 0.0710. All right. State the environmental consequence of releasing sulfur dioxide into the atmosphere. So what is the environmental consequence of sulfur dioxide being released? If you guys remember, sulfur dioxide is the formation of sulfur trioxide is catalyzed by oxides of nitrogen. Do you guys remember these two equations? So here, for example, nitrogen dioxide is catalyzing the formation of sulfur trioxide, right? And what happens is that now sulfur trioxide reacts with water to form sulfuric acid. Okay, so therefore we can say that it contributes to the formation of acid rain. Okay, sulfur dioxide can be removed from air by reacting it with sodium hydroxide aqueous. Construct an equation for the reaction of sulfur dioxide with sodium hydroxide aqueous. Include state symbols. So what we have here is we have sulfur dioxide, right, reacting with sodium hydroxide aqueous. Okay, now if you guys remember, sulfur dioxide, the anion that it produces is the sulfite ion. Okay, and sulfur trioxide, the anion that it produces is the sulfate ion. Okay, this is sulfate 6. Okay, this is sulfate 6 over here, and this over here is sulfate 4. All right, or a sulfite ion. So over here, what you're going to produce is you're going to produce sodium sulfite or sodium sulfate 4. So we're going to produce Na2SO3. And if you guys remember, sulfur dioxide is an acidic gas. It's an acidic oxide. So it will also neutralize sodium hydroxide. We're going to produce salt and water. Okay, and this is aqueous, the salt, and water is obviously a liquid. And for this, you're going to need 2 moles of NaOH. Next question that we have is question number 2. The reaction scheme shows some reactions of calcium. In the first reaction, calcium reacts with nitric acid to form calcium nitrate. Right? Reaction 1 produces calcium nitrate and one other product. So what's the other product that's formed? You have a reactive metal, calcium, reacting with an acid. So what are you forming? You're going to form salt and hydrogen gas, right? When acids react with reactive metals, you form salt and hydrogen gas. So the other product over here is hydrogen gas. Okay, H2. Construct an equation for the thermal decomposition of calcium nitrate. If you guys remember, calcium nitrate की जब decomposition होती है, we produce calcium oxide, nitrogen dioxide, and oxygen gas. Okay, and if you want to balance this, calcium is already balanced over here, so you have 2 nitrogens over here, so you'll have 2 NO2, and then at the end we're going to balance the oxygen, so we have half O2. Okay, you can write the whole numbers as well, or you can write it in fractions. It doesn't matter, they're both acceptable. State the trend in thermal stability of the group 2 nitrates down the group. So down the group, what happened to the thermal stability of the nitrates? Is it harder for them to decompose or easier? Down the group, more heat is required to decompose the nitrates. So it's more difficult to decompose. So we can say that the thermal stability increases. We can say that thermal stability increases down the group. Okay. Why that happens as part of your A2 theory. In reaction 3, excess carbon dioxide is bubbled through water containing calcium carbonate. A solution of calcium hydrogen carbonate forms. Construct an equation for this reaction. So over here they're saying in reaction 3, if CO2 is bubbled through calcium carbonate, you form calcium hydrogen carbonate. Okay, and you just have to construct an equation for this reaction. So what they're saying is that if you have calcium carbonate to begin with, and you have water, right? And if you bubble carbon dioxide through it, you form calcium hydrogen carbonate. Okay, I haven't done anything here. All I've done is I've taken calcium carbonate in water, I've added carbon dioxide, and I've formed calcium hydrogen carbonate. And this equation over here is balanced. Okay, Describe how calcium hydroxide is used in agriculture. If you guys remember, calcium oxide and calcium hydroxide can be used in agriculture. So same with calcium carbonate, because they're basic or they're alkaline, right? The solutions are alkaline. So what it does is it actually reduces the acidity of soil, or we can say it is to increase the pH, okay? You can also say increase the pH of soil. All right. In reaction 4, calcium carbide is formed from calcium oxide. Calcium carbide contains the carbide's C22- ion. Each carbon is sp hybridized. Describe how sp hybridized orbitals form. Describe how sp hybridized orbitals form. So the key word here is how. So how do sp hybridized orbitals form? They form when 1s orbital mixes with 1 p orbital, okay? They're not talking about when they form or why they form. They're simply asking how they form. How they form is when 1s orbital and 1 p orbital mix together. Sketch a diagram to show how two sp hybrid orbitals can form a sigma bond. Now, this is actually a question that has never shown up before in the past papers, okay? Normally they don't expect you to be able to draw hybrid orbitals, but we'll draw them, okay? Now, normally speaking, when you draw a p orbital, right, this is what a p orbital looks like, and this is what an s orbital looks like, okay? Now, when we form sp hybrid orbitals, okay, they're going to look like a mixture of the two, so sort of like this, okay? It's sort of the p orbital, but it becomes more spherical because it's combining with an s orbital, okay? So this is an sp hybrid orbital. Understand that sp2 will also look similar, but it won't be as spherical, okay? So for example, if you look at sp over here, you can say sp would look like this, okay? Sp would sort of look like this, right? Where something like sp2 would actually look like this, and sp3 would even look less spherical, okay, like that. But the idea is that they become slightly more spherical on one of the lobes becomes slightly more spherical. So this is what sp would look like, this is what sp2 would look like, this is what sp3 would look like, okay? I mean, they basically look similar, but the idea is that when an s and a p orbital combine, the shape is sort of, it's still double lobed, but it sort of becomes more spherical on one side, okay? So this is what a hybrid orbital looks like. Now the question is saying, how do two sp hybrid orbitals combine to form a sigma bond? So let's say that I have one sp orbital here, right? And I have another sp orbital over here, right? And here I have the nucleus. Now when these two orbitals combine, what do I end up making? I end up making a sigma bond. Like that, okay? So now I've made a sigma bond between two sp. So these two are sort of overlapping with each other to form a sigma bond. They're forming a head-on overlap, okay? So over here, you would clearly need to show two hybrid orbitals combining to form a sigma bond, okay? That is head-on overlap between these two orbitals. All right. The flowchart shows some reactions of CaC2, that is calcium carbide, right? Reaction 5 can be used to prepare NH3. So reaction 5 is when this guy reacts with H2O to form calcium carbonate and NH3. Calculate the minimum mass in tons of calcium cyanamide, that's CaCN2, okay? Calcium cyanamide, that is required to produce 1.50 times 10 to the power of 6 tons of NH3. So what we want to do is we want to produce 1.5 times 10 to the power of 6 tons. So that would be times 10 to the power of 3 kilograms times 10 to the power of 3 grams. In other words, that would be 1.50 times 10 to the power of 12 grams. Okay. Tons to kilograms, you multiply by 1,000. Kilograms to grams, you multiply by 1,000. So now we can find, now that we have the mass of ammonia that we want to form, right? we can say that the number of moles of ammonia is equal to the mass divided by the molar mass. So that would be 1.50 times 10 to the power of 12 divided by the molar mass, which is 14 for nitrogen plus 3, right, for the 3 hydrogen. So that's 17. So what's the number of moles of ammonia that we want to produce here? So this is equal to 8.82 times 10 to the power of 10 moles of ammonia. We want to figure out the mass of calcium cyanamide that we need. So we want to figure out this mass. So now that we have the moles of ammonia, we can compare the molar ratios, right? For part 2, we can say for every mole of CaCN2, 2 moles of ammonia are produced. Right? So if I have 8.82 times 10 to the power of 10 here, how many moles of this do I have? This is equal to 4.41 times 10 to the power of 10 moles, right? We're going to have half as many moles. For every 1 mole of calcium cyanamide, we're going to produce 2 moles of ammonia, right? So we'll have half as many moles of this. So then I can figure out the mass. I can say the mass of CaCN2 is equal to the number of moles times the molar mass. The number of moles is 4.41 times 10 to the power of 10. And the molar mass over here is, Ca is 40.1 plus carbon, that's 52.1, right? Plus 2 nitrogen, so that's 28 plus 52.1, so that's 80.1. Okay. So what's the mass over here? We get 3.53 times 10 to the power of 12 grams. Now, if you want to convert this to tons, we divide by 10 to the power of 6. We multiply it by 10 to the power of 6 here to convert tons to grams. We divide by 10 to the power of 6. So we get 3.53 times 10 to the power of 6 tons. Okay. Draw the structure of the organic products formed in the following reactions. So when bromoethane reacts with NaCN dissolved in ethanol, what do we make? Does anyone remember what's the mechanism for this reaction? When NaCN and ethanol reacts with a halogenoalkane, this is nucleophilic substitution, right? The cyanide substitutes for the bromide over here, and we form propane nitrile. We form a 3-carbon compound. So we go from a 2-carbon compound to a 3-carbon compound, right? The cyanide substitutes for the bromide. Now, how do we convert when the nitrile reacts with acid? What do we form then? What happens to the nitrile when it reacts with acid? Dilute H2SO4 under heat under reflux. This is hydrolysis of nitriles, right? So we end up producing a carboxylic acid. This is acidic hydrolysis. And if I react this ketone, it's propanone, with NaCN and HCN, what do I produce? Does anyone remember what the mechanism for this reaction is? When carbonyls react with HCN, this is nucleophilic addition of HCN. NaCN is a catalyst, right? NaCN provides the cyanide ions for the reaction. It's a catalyst, okay? So this is addition of HCN, and this is a nucleophilic addition reaction. So what you have is you have H and you have CN over here, okay? So that's your product. Next question that we have over here is question number 3. Phosphorus is a reactive period 3 element. Phosphorus has several allotropes. Details of 2 allotropes are given. Again, allotropes are basically 2 different ways in which the same element can exist. So for example, allotropes of carbon can be diamond, graphite, Buckminster fullerene, right? Here they said we have 2 allotropes of phosphorus. We have white phosphorus, which has this molecular formula P4. That's the one you're familiar with. And we also have red phosphorus that we use in a lot of organic chemistry reactions. And the melting points are given to us, right? The melting point of white phosphorus is 44 degrees Celsius and red phosphorus is 590. Now they both have covalent bonding. Suggest the type of structure shown by white phosphorus and red phosphorus and explain why red phosphorus has a higher melting point than white phosphorus. So first of all, if you think about white phosphorus, that's P4, what do you think the bonding over here will be? Or what do you think the type of structure will be? We have covalent bonding, but what type of a structure will it be? Would it be simple molecular or giant molecular? It has a very low melting point. So this would be a simple covalent or a simple molecular structure. Okay, it has a simple molecular structure. Okay, and what about red phosphorus? It has a much higher melting point. It also has covalent bonding, but it has a much higher melting point. So what type of a structure would that be? That would be a giant covalent or a macromolecular structure, right? So we can say giant molecular, or we can say macromolecular structure, or giant covalent structure. They're all acceptable. Okay, giant molecular structure. And explain why giant molecular structures have much higher melting points than simple molecular structures. The reason why is because in P4, in the simple molecular structure, right, van der Waals forces or weak intermolecular forces, right, weak van der Waals forces between molecules have to be overcome. Whereas in red phosphorus, which is a giant covalent structure, right, strong covalent bonds have to be broken, okay, in order to melt it. Have to be broken, okay, in order to melt it. So a lot more energy is needed. How do we know that it has a giant molecular structure? Based on the evidence. They said they both have covalent bonding, but one has a very low melting point, the other has a fairly high melting point. Now, what kind of a covalent structure will have a high melting point? It'll be a giant molecular structure. Okay? Yeah. Red phosphorus forms when white phosphorus is exposed to sunlight. Use this information to draw a reaction pathway diagram to show the formation of red phosphorus from white phosphorus. So for a reaction profile diagram, right, all you have to do is, first of all, when we expose it to sunlight, the sunlight provides what? The sunlight provides the activation energy, right? The sunlight provides the activation energy, and then the overall reaction is exothermic, so the products are actually lower than the reactants here. So here you have P. Okay? So this is your red phosphorus, and here you have your white phosphorus. Okay, and obviously here you have your activation energy, and here you have your enthalpy change given to you, which is negative 17.6. Some reactions of white phosphorus, that's P4, are shown. State the oxidation number of phosphorus in P4O10. Now, if you guys remember, this is phosphorus 5 oxide. So what's the oxidation number of phosphorus here? You guys should remember that the oxidation number of phosphorus here is +5. But you can calculate it as well. We have 4 phosphorus, so we have 4x, and we have 10 oxygens, and each oxygen is -2, and this is equal to 0. So we can say 4x is equal to 20, so x is equal to +5. Okay? In case you guys forget, you can always calculate it. Deduce the identity of Q and hence construct chemical equations for reactions 1 and 2. So they're saying over here we have Q, right? Q can be formed when PCl5 reacts with H2O. It can also form with P4O10, or phosphorus 5 oxide reacts with H2O. So what do you think Q over here is? What happens when the oxide of phosphorus or the chloride of phosphorus dissolve in water? What are we forming here? We have an acidic oxide and an acidic chloride. So what acid do we think we're producing here? Q must be, anyone remember? Q must be phosphoric acid. Okay, phosphoric 5 acid. Phosphorus has an oxidation state of +5 here. So we're forming the phosphate 5 ion. Okay. With PCl5, you also produce HCl. But the common product for both is phosphoric acid. So if we had to construct the equation, for PCl5, we produce HCl and H3PO4. And if we balance this, right, what do we have? We have 5 chlorines on the left, so we have 5 HCl here, right? And we have H3. And obviously, if we're going to balance the waters over here, we have 8 hydrogens on the right, so we're going to have 4 H2O on the left. So that's the balanced equation. And when P4O10 reacts with water, you only produce phosphoric acid, phosphoric 5 acid. So that is H3PO4. And again, we want to balance the equation over here. And the balanced equation, you should just remember this balanced equation. What you're going to have is you're going to have 6 H2O here, and you're going to have 4 H3PO4. The next part of the question is part C, which says the triphenylphosphine is used in a type of reaction known as a Wittig reaction. So we have triphenylphosphine here, where this ring over here has the formula C6H5. Right? This is a benzene ring. This is something you'll get more familiar with in A2. Give the empirical formula of triphenylphosphine. So here we have 3 of these, right? We have 3 of these C6H5 rings. So that would be C18H15, right? And then we have P, right? And then we have a P over here. So what we have is we have C18H15P. That's the empirical formula. Now, in a Wittig reaction, an aldehyde reacts with a halogenoalkane to form an alkene. This conversion is shown in the following unbalanced equation. Okay, so here you have an aldehyde reacting with this halogenoalkane. In this case, you have an iodoalkane, right? In the presence of triphenylphosphine, that's what we saw in the previous part, and a strong base to form this type of a product. So the aldehyde is being converted into an alkene, okay, using a halogenoalkane. Aldehyde and halogenoalkane are being converted into an alkene. Don't worry about how this, we're just going to see how this reaction works, okay? This is not a reaction that they expect you to know beforehand. They've given you this information in the question, okay? Compound H can be made from propanal, that's C2H5CHO. Stage 3 in the reaction scheme is a Wittig reaction, okay? So we're going to get to stage 3 in just a bit. Now in stage 1, the aldehyde reacts with NaBH4 to form G. So what kind of a reaction is stage 1? State the types of reaction that occur in stages 1 and 2. So what's the reaction that's taking place in stage 1? When an aldehyde reacts with NaBH4, this is called a reduction reaction, and you're producing a primary alcohol. Okay, so here you're producing C2H5CH2OH. The aldehyde is being reduced to form a primary alcohol. Okay. In the second step, in stage 2, that primary alcohol reacts with red phosphorus and iodine to form a halogenoalkane, an iodoalkane over here. What type of a reaction is this? When iodide substitutes for OH over here. This is a substitution reaction, right? Or nucleophilic substitution. Okay. Nucleophilic substitution. They'll accept substitution as well, but this is a nucleophilic substitution reaction. Halogenoalkanes to alcohols is nucleophilic substitution, and alcohols to halogenoalkanes is also nucleophilic substitution. Draw the structures of G and H in the boxes provided. Now, we already figured out the structure of G. We said G was a primary alcohol, so that would be C2H5CH2OH, right? We've already figured that out over here. Although I would be inclined to say CH3CH2, okay? I would be inclined to say CH3CH2. So that would be a better structure to draw here. Okay. And we also have to draw the structure of H. Now, how do we draw the structure of H? Now in H, now let's go back to the Wittig reaction for just a second. What happens in the Wittig reaction? Let's see. If you look over here at R1, R1 is bonded to the carbonyl carbon. So in this Wittig reaction here, what is R1? What is this R group that's bonded to the CHO? What is the R group bonded to the CHO over here? Can someone tell me? We have the CHO group here. So R1 must be the ethyl group, right? R1 is the ethyl group. So let me write that down. We have R1, right? And R2 is bonded to the CH2I, right? You have a CH2I here, okay? And R2 is the group that's bonded to the CH2I over here. So what is R2 over here? What's bonded to the CH2I? We have the CH2I. So what's bonded to that? What's R2? R2 is also a ethyl group, right? This is R2. C2H5 again. And now if you look at the product of the reaction, what do we have? We have R1. That was bonded to the carbonyl carbon. That carbonyl carbon is now an alkene. And same with the carbon that had the halogen, right? The carbon that has the halogen, and the carbon that has the aldehyde, those two carbons bond together to form an alkene. I'm going to label those here. This carbon here and this carbon here combine to form an alkene, right? So the product of this reaction in this particular case, when you look at H, you have R1. So that's C2H5, right? That C2H5 is bonded to a CH. That's bonded to a CH, double bond. And then that is bonded to another CH. That's bonded to another CH. That's bonded to R2. And R2 over here is also an ethyl group. So that's C2H5. So that is the product of this reaction. Okay. So this is our product H over here. What we form is, we form C2H5, CH, double bond, CH, C2H5. Identify the organic products formed when compound J, shown below, is reacted with hot concentrated acidified manganate 7 ions. So you have an alkene that's reacting with hot concentrated acidified manganate. We have sulfuric acid. That means we just have acidified manganate, right? So what happens here? What type of a reaction is this? Does anyone remember? This reaction is strong oxidation of alkenes, right? So what we're going to do is we're going to rupture this double bond. Now, if you look at the left, right? If you look at the left-hand side, right? This product here, this carbon is bonded to one hydrogen. So what does this carbon end up becoming? What kind of a functional group do I form on this carbon? Right? This carbon here. Okay? This becomes a carboxylic acid because it has one hydrogen. So this, where this double bond was, becomes a carbon oxygen double bond, right? This C becomes a C double bond O. The H becomes an OH, and then we have CH3, CH2. So what we end up making over here is, we end up making propanoic acid. And what's the other product over here? This carbon is bonded to two carbon atoms. So it will end up becoming, this C will become a C double bond O, right? And now what we're going to end up with is a ketone. So if the carbon on the double bond is bonded to two carbons, it becomes a ketone. If it's bonded to just one carbon and one hydrogen, it ends up becoming a carboxylic acid. And what if there were two hydrogens? Just in case. What if there were two hydrogens? Then what would you make? So here you're making this ketone here, right? But what if there were two hydrogens? Then what would you make? Then you would make carbon dioxide and water. Okay? All right. Last question. Compound B is a liquid with a fruity smell. So here we have compound B. Fruity smell because it's an ester, right? We have an ester linkage over here. That's where the fruity smell comes from. The reaction scheme shows how B can be made from ethanol. Okay. Reaction 1 is an oxidation reaction. So here we're making compound B. We're starting with ethanol. They're saying reaction 1 is an oxidation reaction. Give the reagents and conditions required for reaction 1. So what we're doing here is we're converting an alcohol, a primary alcohol, to a carboxylic acid. So what are the reagents and conditions that we're going to use here? We can use acidified manganate or we can use acidified dichromate, right? We can use acidified dichromate. That's the oxidizing agent. And what are the conditions? For this particular reaction, you can't say heat. You have to specifically say heat under reflux. What if I heated and distilled the product? Then what would I make? If I did heat and distill, what would I make? For a primary alcohol, if I heat and distill with dichromate, I make an aldehyde. If I heat under reflux, I make a carboxylic acid. So here you have to specify heat under reflux, okay? You have to specify heat under reflux, okay? Construct an equation to represent reaction 1. Use O to represent an oxygen atom from the oxidizing agent. So what we have here is, we have, just write it the way they've given it, right? We have C2H5OH, right? But I'll just write CH3, CH2OH instead, because for the product we're going to need that. And for oxidation to a carboxylic acid, you're going to need 2 oxygen atoms. And you're going to end up making CH3, CO2H. So what's happened here is that one of the oxygen atoms adds on, right? The primary alcohol is oxidized to a carboxylic acid, and the 2 hydrogens are removed by the other oxygen atom. So we have plus H2O, right? 2 hydrogens are also removed here from here. So we have plus H2O. So yeah, 2 oxygen, one is being added, and the other oxygen is removing the 2 hydrogens to form water, okay? Suggest the type of reaction that occurs in reaction 2. So what's the type of reaction in reaction 2? What we have is a CH is substituted by a bromine. A CH is substituted by a bromine. So what type of a reaction is that? On a saturated carbon. On a saturated carbon, if a hydrogen is substituted by a bromine or a halogen, that reaction is a free radical substitution reaction, right? That reaction is a free radical substitution reaction. Okay. H2SO4 acts as a homogeneous catalyst in reaction 3. Explain why H2SO4 is described as homogeneous. Now, if you guys remember, homogeneous catalysts are catalysts in the same state. Okay, it is in the same state. It is in the same phase or in the same state. Same phase or in the same state, right, as the reaction mixture. So if you look at the reaction this is esterification, right? We have liquids. We have, with this carboxylic acid is a liquid, ethanol is also a liquid, and H2SO4 is aqueous, right? So it's in the same state. On the other hand, for example, reduction of alkenes, when we use hydrogen and nickel, nickel is a heterogeneous catalyst because nickel is a solid and the reactants are gases. So if the catalyst is in the same state as the reactants, so if it's aqueous, for example, with liquid reactants, it would be called homogeneous. If the catalyst state is different from the reactants and the products, then it's called a heterogeneous catalyst. Reaction 2 needs to take place in the absence of water to prevent formation of compound C. So here we have compound C, right? And what they're saying is that if we have reaction 2, if you look at reaction 2, they're saying if water is present, then the bromine will be converted to an alcohol, right? This will become an OH instead. This will become an OH instead if we have water present. If water is present, right, what we'll have is hydrolysis of the bromoalkane. Okay. All right. If C is present in the reaction mixture of reaction 3, a different compound D, will also form. Compound D has 2 identical functional groups. The infrared spectrum of D shows strong absorptions at 1100 wave numbers and 1720 wave numbers, but no absorption due to OH bonds. Use the data booklet to identify the functional group present in D. Explain your answer as fully as you can. So they're saying over here that if you take this compound, this is compound C, right? And if compound C is present in the reaction mixture of reaction 3, so if this compound is present in the reaction mixture of reaction 3, so in other words, if this compound is present over here, right, what we're going to end up making is a different product altogether. Okay. Now, so if, for example, if this compound is treated with concentrated H2SO4, if this compound is treated with concentrated H2SO4, what's gonna be made? Anyone? They're saying the infrared spectrum of this compound, the resulting compound D, has absorptions at 1100 wave numbers. This is due to the C single bond O, and 1720 wave numbers. This is due to the C double bond O. What they're saying is that if this guy, okay, this compound C, right, if it was present with concentrated sulfuric acid, it would make D, and D would have a C single bond O and a C double bond O. Now this data will obviously be given to you in the exam, right? So what you have here is at around 1100 wave numbers, you have the C single bond O, okay, and around 1720 wave numbers, you have the C double bond O. So what group do you think is present? What group do you think is present over here? We have C single bond O and C double bond O, but you don't have OH group presence. It must be an ester linkage. It must be an ester linkage. And I'll actually show you guys how we get an ester linkage here, okay? I'll actually show you guys how we get an ester linkage over here. So what we have over here is, okay, let me just show you guys this. What happens here is this. If you take this guy and you react it with concentrated H2SO4, you react this with concentrated H2SO4, what do you get? What you get over here is this, right? What you get over here is this. You get self-esterification. Do you guys remember this? You have this acid group over here, right? And this guy has an OH. And if this combines with another molecule of the exact same type, if this combines with another identical molecule like this, you end up making a cyclic diester. Does everyone remember this? The acid loses the OH and the alcohol loses the H over here, right? So, and what you end up making over here is the following ester linkage. What you end up making is this compound here, C double bond O, then you have O, then you have this guy, then you have this guy, okay, and then you have this. Have you guys learned this? You can have self-esterification take place, right? You can have self-esterification take place over here, okay? So what can happen is two molecules of the same type can combine to form an ester, to form a diester. So that's actually the reaction that takes place here. If over here what happens is that if this compound C is present, with concentrated sulfuric acid, right, you end up making a cyclic diester. So over here what must be present is an ester linkage. What must be present is an ester linkage, okay? And we can say that the absorption that we see at 1100 wave numbers is due to the C single bond O, and at 1720 wave numbers, we have the absorption due to the C double bond O, okay? And what happens is that the CO2H and OH, okay, the CO2H and the alcohol in compound C combine to form an ester. Okay. So the carboxylic acid and the alcohol combine to form an ester. So you have self-esterification, basically not self-esterification, but you have two identical molecules. Because this molecule has an acid and an alcohol, it can combine with another molecule of the same type, okay? It can combine with another molecule of the same type to form a cyclic diester, all right? Which would look like this. So that's the reaction that's taking place over here. That's the reaction that's taking place over here. Some other reactions of C are shown. Okay, C can react with sodium carbonate to form compound E. Draw the structure of E. So what group in C will react with sodium carbonate? Sodium carbonate is a base, so it will react with the carboxylic acid to form salt, carbon dioxide, and water. So the structure of compound E, that will be the organic compound, right, will be this. What we're going to end up making is a sodium salt of the carboxylic acid. Okay, and then we have the alcohol that remains unreacted. Okay. Next part says, suggest why NaBH4 is not a suitable reagent to make F, which is CH2OH twice from C. Explain your answer. So what they're saying is, what you're doing over here is you're reducing the carboxylic acid. You're reducing the carboxylic acid to form ethane 1,2-diol, right? Now, why can't we use NaBH4? Right? For reduction of carboxylic acids, we can only use lithium aluminum hydride. And the reason we can't use NaBH4 is because it is not a strong enough reducing agent. Not a strong enough reducing agent. Okay? You need to use lithium aluminum hydride. Construct an equation for the reaction of CH2OH twice with SOCl2 to form G. So they're saying construct an equation for this reaction. Now, if you had to construct an equation for this reaction, guys, what you're just going to do over here is first you have this compound that's reacting with SOCl2 to form CH2Cl, right, twice, right? So what's happening is that the chlorine, remember this is nucleophilic substitution, the chlorine is substituting for the OH over here. And what's left over here, what we have is we have OHs, right? We have two OHs, right? And we have an S and an O. That's what's left over, right? So what we have is, what are the possible products that we can form? Well, over here we can form sulfur dioxide and water, okay? And the reason why is because this is not a redox reaction. So sulfur will still have an oxidation state of +4. And SOCl2, the oxidation number of sulfur is +4. And the product, we know that the only product that's possible over here that has an oxidation number of +4 is SO2. Okay? So over here, you're not going to produce an acid. You're just going to say SO2 and H2O over here. Okay? You're not going to combine these two together. All right? Explain why C is very soluble in water. The reason why C is very soluble in water is because it can form hydrogen bonds with water. Okay? It can form hydrogen bonds with water because it has a carboxyl group as well as an alcohol group.